So let's get started. This is the first town hall for Brick by Brick Challenge, and we have the challenge organizers Matt Amos and Arian Prabowo with us. And the quick agenda is that first we'll go through the mission statement, the purpose of this challenge, and details on how this data was collected and processed, and a little bit of background on BMS. Then Arian will cover discussions on data set, the splits and statistics. We have received quite a few queries on about it on the community forum, so we'll dive into them deeper, and he'll also address the problem formulation and the benchmarking methods that I used. At the end of these two presentations, we'll have a Q&A session. The questions you have dropped in the chat box, or you can raise your hand and unmute and ask the question. And then eventually we will cover some of the questions from the post from the Discourse Community Forum. And that's the flow. All right, let's get started. A little bit about both the organizers and the panelists for today's town hall. Aryan is a researcher at University of New South Wales in Sydney. He specializes in building time series datasets. And in this town hall, as discussed before, he'll be covering the dataset preprocessing and matrix and baseline methods and potential future ideas on how you can improve your solution for the next round. Matt is a senior data scientist at Commonwealth Scientific and Industrial Research Organization, and his work focuses on sustainable energy practices, building digitization, and reducing the costs associated with it. And with that, just a second. With that, I request Matt to start with his first presentation of the day.
Thank you, Sneha. Can you see that? That's all
yes.
good?
Yes, all
Beautiful. Good. All right. Hello, everyone. Thanks for coming tonight, today, or whatever time it is for you. Yes, I'm Matt Amos, Senior Data Scientist at CSIRO, which is Australia's National Science Agency. And I am working with UNSW to bring you this challenge. So yeah, as Sneha mentioned, I'll be doing a quick overview of the challenge, some background context about why we wanted to run this challenge and what it means and what it could lead to. And yeah, the context from CSIRO as well as UNSW as well. So just a quick acknowledgement around the challenge and the project related to this challenge. So it's part of the CSIRO-led New South Wales Digital Infrastructure for Energy Flexibility project, and is funded by both the New South Wales Government and Race for 2030 CRC. We do have a few other collaborators within the call as well, so shout outs to them, both from the UNSW and the University of Wollongong as well. So I wanted to kind of start this off by giving you an example scenario, which hopefully will spell out why this problem is actually useful. So the scenario is that you're an application developer. You have created some software which reports on building energy use, and it suggests changes to usage behavior to actually reduce the energy footprint of your building. The application requires energy consumption data, so that's the actual load of the building, as well as generation data if that exists, and occupancy data for the building as well. So in this example, for one building, this is quite simple. You can look up the exact details of the building and make your software tailored to that building itself. But then your application is so successful that you have interest from a new set of building owners to use the application on their buildings. Each building is different and distinct and unique, including both the topology and the number and the types of sensors and meters. So some may have generation, some may have occupancy sensors, and some may not. And you have to, the challenge is, how do you actually make sure that your software is redeployable on these different buildings and have it run on these buildings and produce a sane output? So one way of solving this problem is using something like a standardized ontology, such as the Brick schema. So the Brick schema, I've put a link to it here for further reading, but it offers a way to describe the contents of a building, and I'm labeling these entities, as well as the relationships between entities in a standardized way. So using something like the brick schema, those three buildings that I had in our scenario, they can look exactly the same or at least described in the same language. So you can redeploy your application using the same language across all three buildings. The definitions for these entities and relationships then form a graph, or also known as a semantic model, which you can see over here on the right. So this is a big web of different parts of the building. And then there's a small example of some of the points within the building. So that's these light blue boxes. And then the relationship to, for example, a location, which is this open office, and various relationships between different locations and equipment as well. These can get quite complicated, so visualizing these can be a bit tricky. But yeah, this model can then be queried using something like a query language such as Sparkle to allow you to actually grab out relevant parts of the building model to use in your application. So in our example, we need a query that gets us the consumption meter, the any generation meter if it exists, and occupancy meters, occupancy sensors as well from our building. Yeah, so as I said, we can now create a standardized query against these three buildings to gather the relevant parts of the buildings without ever having to actually know the uniqueness or the specific layout of these buildings themselves. But how do we actually generate the semantic model for these buildings? What's the process look like for doing that? So taking a step back before we get to the semantic models, this challenge is obviously about the time series data. Within smart buildings, we have lots of types of time series data coming from different sources within the buildings. So things like meters, commonly energy meters, gas or water meters, and also heat meters for things like district heating, which is quite popular in Europe. As well as you have Internet of Things sensors, which have become quite ubiquitous these days. So things measuring such as temperature, humidity, light, motion, and indoor environment quality as well. As well as occupancy, which is relevant to our example, and other devices such as alarms, batteries, EV chargers, and HVAC, which are quite common within these buildings as well. So these sources are commonly connected to a building management system or BMS, or to external APIs, which then allows you to actually extract that time series data into something like a data platform or just onto your local system to run your application. And this could be via MQTT or via REST API, for example. There's lots of different ways that you can get that data out of those systems. So once we have the time series data coming into the platform, taking another step back. So yeah, one of the things that I do work on at CSIRO is the data clearinghouse, which is a digital platform which fuses together the time series data that I was just talking about and the semantic data. So the brick schema or the brick models, the semantic models about buildings to allow, for example, for energy and cost saving applications to be run on your building data. Among other things as well, but yeah, that's just an example. So the way that DCH does it, and I'll do a little bit of a case study on DCH, DCH connects to these systems, for example, via MQTT or REST API to get this time series data into the platform and allows users to construct the semantic models of their buildings by, firstly, it automatically creates brick point entities. So that's kind of like the default or the minimum information you need about a point, which is basically a representative of some time series data coming into the system. Secondly, it allows for manual or rule-based classification of points, which I've underlined here because that might be quite interesting to everyone in this call. If you might have a suspicion that this might be where the challenge is actually directed to, and you're exactly right. So this is the part of this process that we've targeted for this challenge, which is, how do we actually classify these points in an intelligent way? And is there smarter ways that we could actually do this rather than manual or rule-based methods? And then thirdly, just to kind of explain the whole process, after the points have been classified, you can then add other brick entities to your model and also include the relationships between different parts of the model. So if energy, a point reading is attached to an electrical meter, modeling that relationship in your model so that it's a full model and you can query relevant parts of it and do some interesting things as well. So stepping through each of these three steps. So firstly, once the data comes in, the time series data comes into the platform, it's detected, and if required, if it's new data coming into the platform, these points will actually be minted or created within the system. So for example, here I've got 5 points. The labels above these points are the identifiers for those points. So you can see we have got an energy meter 01, which has a power kilowatts point. So some time series data relating to power coming in here. We have another power kilowatt reading for energy meter 02. And then we also have a temperature, humidity, light, and motion sensor 01, which has a relative air humidity reading here. It also has an occupancy reading here, which is interesting to us, and then a luminance reading here as well. So there's different readings coming from the same sensor and also similar readings coming from different meters as well. But right now, these are all just the generic brick class. So we don't really know, you might be able to guess what they are based on the names, but we don't really know what they are in the system yet. So then to actually give more meaning to these points and have them be useful for an application to request, we go through the point of classifying these points to give them a more specific definition and allow us to actually query them later on. So one example rule, you could look for anything that ends with power kilowatts and classify that as a brick power sensor. Similarly, for the relative air humidity, you could tag it as a return air humidity sensor. And then similar for occupancy sensor and luminance sensor as well. So the gotcha here is that this relies on these names being consistent. So in our example, we had 3 different buildings. There's nothing to say that those 3 different buildings will have the same way of naming their points. They could be different organizations, different onboarding parties that actually linked up the data to the platform. So it is fraught, but it is a way of actually classifying these readings that we do get in from the equipment. And then thirdly, we have the extra bit. This is adding the extra entities and relationships to our model as well. So now that we've got our classified points, we've added some equipment. So for example, we have the temperature, humidity, light, and motion sensor 01, which we've called a brick sensor equipment. And then we have their 2 electrical meters, which we've said are all on the same floor. Obviously, this is a fairly simple model, but it does get very complex as you do go to large scale buildings, which have lots of types of sensors and locations within them. So yeah, once we have this complete model, it allows us to do complex queries and actually get some of the more interesting parts of the model into our application. For example, relevant to our scenario, find all electrical meters which also have occupancy sensor data linked within the same location. Obviously, it won't be a plain text human readable form like this. It'll be a complex Sparkle query, but that's the gist of what the query could look like. So now that we have our points classified, either by a rule or manually classifying each point individually, we can create that query and get the relevant data from our buildings. But this is a time-intensive process and requires a lot of manual work. What if there was a more efficient way through automation, which is basically the question for this challenge. So the mission statement comes out to be to reliably automate building data classification, increasing the accessibility and efficiency of building model creation. And so with that, I will pass over to Ariane who talk about the more technical side of the competition. And thank you for your time.
Should I just I'll start, I suppose.
Yeah.
All right. Thank you very much, Matt. Wait, sorry, wrong button. Um, Thank you very much, Matt and Sneha. I'll just go straight to this. Um, right. So, welcome everyone to the second part of the town hall. I'm Aryan Prabowo, a postdoc in UNSW. Um, so let's get straight into it. Um, today I'm going to talk briefly about the technical aspect of the data set and briefly talk about the technical aspect of the challenge. The data set, let's just go into it. A brief summary. This is coming from three buildings in Australia, and it spans 3 years. It has more than 15,000 time series, and originally it has more than 300 classes, and it comes with the metadata that describes how the different time series are connected. Um, yep. So here are the examples of the 6 time series. The data set is very interesting and very different. If you're familiar with other time series data set, this is quite unique because it has a very diverse class and distribution had to be expected, right? So for example, temperature sensors, these twos, the two in the middle, will have normal or log normal distributions. It will varies. I suppose this is in Celsius. The one indoors will varies between 20 and 25. Understandably, the one outside will varies between 10 and 40. And as expected in Australia. Um, However, other things, for example, like status, the one at the bottom, the status only have two values, on or off. So this will have more of a Bernoulli distribution instead of a normal distribution. Alarms is even more interesting. We don't have any alarms here, but as you can imagine, it is also like Bernoulli, like status, but it would not be balanced. Like most of the time, it will be off, and only once in a rare time it will turn on. It will be on. Um, and and set points behaves more like an event rather than giving a continuous value. For example, here usually we set the set point at your own home, I suppose. You set your air conditioning set points at certain value, and then you leave them for a long time until you turn them off, or it gets too hot or it gets too cold, right? So you will have a lot of very steady horizontal values in set points, and some time series, just because the way this IoT devices are set up, some are monotonous. So, for example, this electrical power sensor in particular is just collecting. It's a monotonous. It's just an accumulating how much power has went through, right? So it's just a, monotonous increase. It should never go down. Another thing about this raw data set is that the time steps are irregular. Some of them, many of them are like every minutes. But some of them are also at every 10 minutes, and they're not exactly on the minute. And yeah, they're not exactly on the minute. And there are also some, and this is to reflect the reality at the ground. There will be some missing data. Even over here, we can see at about late June, right? Over here, late June, there's a missing data, and therefore there's a zero spike at all different time series. There's a zero spike because there's a missing data there. This is the kind of quality that you can expect from an actual uh, from an from an actual data set from a real life operation data. Um, yep. Here it also comes with the metadata. So as Matt has explained before, every single time series is labeled based on a very exact an industry standard way to label time series in buildings. Um, what we use and we use the brick schema. You can go to the website to see what's inside, but we use an older version, and the documentation to the older version is in this website, which is available in the AI crowd challenge page. um, However, only one building is available. So I'll get into the reason why later on. And this is the summary statistics of the three different buildings. Yep. So briefly speaking, that is what the data looks like. Next is what I did with the data in order to make it into what you see in this challenge. So every all of the information is I think if you go to uh, a lot about the information is available in the starter kit. If you go to the starter kit, it will link to this GitHub webpage, and a lot of information is available here. So including the nearest paper that have all of the details. So for example, we have this image here. So let's just get into it. Let's just go into the problem statement and evaluation metrics. Over here, this is in a certain sense, this is basically a simple classification task. You have a time series, you have a single time series ranging between 2 to 8 weeks in length, and the goal is to create an algorithm, a classifier that will classify what kind of time series is this. But the way this is labeled, um, this is a multi-label setup. So that means that each time series can have more than one labels. So this is not just either sensor or power sensor. It is both sensor and a power sensor. And the reason is, if you go to the brick, uh, if you go to the brick website, the documentation, all of this all of this time series are all of the labels. All of the labels are arranged in a hierarchy. So, for example, the top hierarchy for time series is points, and then under it there are 6 different labels: alarm, command, parameter, sensor, set point, status, and sensor being the and under sensors there are many different kind of sensor. And under, so for example, in this case, it's a power sensor and electrical power sensor, right? So it is an electrical sensor. Um, so it's a power sensor. It's a power sensor, and it's an electrical power sensor. There you go. So the idea is the way the time series are labeled, it is not always labeled at the. So if you imagine this is a tree, it is not labeled at the leaf. Sometimes it's labeled at the branch. Sometimes it's labeled at the branch, right? So in this case, we know this is an electrical power sensor, but we don't know if it is an active or peak or reactive power sensor, right? And this is the way, and 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 the reason is hiring engineers to label all of this 1,000 and 10,000 sensors in the building is very costly, and so they're not always labeled at the best resolution, but only at the sufficient resolution to operate the building. And this is what we can expect. This is what we can expect from a typical building. So that means, if we that means when we get a time series, when we get time series, we don't know. Sometimes it's only labeled as sensor or just power sensor or electrical power sensor, and the motivation is we want to encourage the classifier in order to make as highest resolutions prediction as possible. But if they go into a higher resolution than us, we don't want to penalize them, right? And that is the motivation of why we establish this multi-level setup. Right. So yes. So this is not. This is so yeah. So this is the setup. Um, then that goes straight to the evaluation setup, right? Oh, so sorry. So that's why when you when you make a guess, you can have so so in the setup, you can have a positive label, right? So for example, you can be sure this sensor, this time series is an electrical power sensor, but what if it is only labeled as so for example, in this case, it is only labeled as electrical power sensor. So over here, we don't know whether it's active, peak, or reactive. So this will have a zero label. That means this is uncertain what the true label is, right? And so the negative label are everything else. Um, and the reason why we have this zero label setup is that um, if you make a guess that is higher resolution than what we have, um, we will not penalize it. That's how the zero label works. Over here at the bottom, in the calculation process, there's a more detailed explanation with an example of how it works. But roughly speaking, that is the spirit behind this labeling structure. Um, next, we are going to talk about the label reduction. So as I said earlier, originally this come with 300 different classes. However, in order to make this more feasible for the participants, we combine some classes and we reduce it into 94 subclasses, which you I believe have seen in the data set. And then yes.
Sorry, Aaron,
Yep.
can I jump in? Yeah, no, I was going to say with that label reduction, that's basically just by taking the children classes and grouping them up with the super classes. It wasn't functionally moving the subclasses into different parent classes, if that makes sense. So yeah, it's basically just moving up the hierarchy rather than across the hierarchy.
Yep. That's right. Yes, absolutely, yes. Next, cleaning and aggregation. Cleaning and aggregation. What we do is we do some cleaning as obvious if the sensor if the system goes down for a long time and we have a lot of missing data, we will cut them out. Another but the more important thing about the aggregation is the way we set up the way we set it up is that we have this let's see what's the best way to do this if we were to go back. We have this 15,000 time series. We bring them from the three buildings and we bring them all into one huge data set. So first we aggregate them. Right. And we want to set this up in sort of we want to set up each rows, each time series into a sort of like easy, medium, hard kind of setup in many different ways. One way we do it is we have three buildings. So in the training data, we have lots of data from one building, about 1 year worth of data, and from building one, and from the second building we have much less late data, which is only about 3 months, which is one season. So the idea is can you make an algorithm that can generalize if you only know information about only information about one season from one building, can you generalize your algorithm to how it might behave on a different season, right? And the other one is if and the third building we even have less data on that, right? So that is the spirit. We also vary the length of the chunks that you get from 2 weeks, 4 weeks to 8 weeks. The idea is what is the minimum amount of data collections that you will need in order to be able to make the correct guess. Yeah. So we also want to explore that kind of directions by having the two chunks, the 2 weeks, 4 weeks, and 8 weeks. So 8 weeks will be the easy, 4 weeks will be the medium, and then 2 weeks will be the difficult setup. Yes. So after we aggregate into the 15,000, we divide the setup this way. Some portion of the data will be in the training. A smaller portion of the labeled data will be in training, and the bigger portion will be in the testing for this reason. Um, and after that, once we make that separation, and then we separate the time series, for example, in the training data set, into smaller chunks, that now you see that range between 2 weeks to 8 weeks. This is what we give you. So this is basically, roughly speaking, the pre-processing that happens from the original 3 years data set into what you can see in your challenge. Um, yes, this is described in uh, this is basically, roughly speaking, what is happening here, in this part, as described here. Um, So we also do some basic things. For example, we remove the timestamp. So all you get is a time series without the timestamp. Without the timestamp. So the idea is, we don't want the participants to be able to take these chunks and then play a jigsaw and then try to figure out, oh well, we're missing this time series. It must be, we have a complete time series from this sensor and we are missing from this sensor, and yeah, we don't want to turn this into a jigsaw challenge, into a data recovery challenge. So that's why we remove the timestamp, and some other things as well. So for example, when we chunks the long time series 3 years into 2 to 8 weeks, we don't there are no overlaps. There are some gaps, especially in the test set. There are some gaps in between the chunks, and there are some random gaps in between the chunks. So it will be very difficult to jigsaw this back, into the full data set. Um, and I think, as some people have noticed, the way this is set up, that means we have a huge amount of features. You have all of the features, in the testing set. However, you don't have the labels. So this is very similar to a semi-supervised or weekly supervised setup, where you have a huge data set, but only a few data points are labeled in yeah but only a few data points are labeled. And this is exactly what we can expect, from a real buildings operation. And the reason is, it is very, to collect the data, you just set up the building, the IoT, and to operate it, you already have all the time series, right? You Because you have to build the buildings and you have built the system. However, the expensive part is to hiring engineers in order to onboard this to a universal metadata system like Bricks. All right, so that is the bottlenecks that we can see in the real world, and therefore I hope that explains why the challenge has been set up, in this manner. Um, and yes, the baseline method. If you go to the paper, roughly speaking, this has a different setup. This use all the 300 classes instead of the one that you see, and there's slight and therefore there's a slight difference in the pre-processing. But ideally, this is the results. Um, and I think, what I want to explain is, based on this. Um, I want to explain what are the different naive methods that I use, to make more sense of these numbers. The 0, 1 basically says, over the 0 1 basically says over here we are guessing negative -1 for everything, for every single one. Everything is -1. Everything is everything. It's nothing. And surprise, surprise, it has a very good accuracy. It has a 95% accuracy, and the reason being is because the data is very unbalanced, right? It is most probably just a sensor, and it's most probably, for example, if it is a sensor, that means it is going back to the brick. It is not. If it's a power sensor, that means it's not everything else, right? So if you just guess -1 for everything, since it's a multi-label setup, you're allowed to do that. You don't have to pick a positive answer. You can get a very high. You can get a very high accuracy. But as expected, the F1 score is 0, and that's why we use F1 score instead of accuracy, because there's a very unbalanced data. Mode is, if you look at the data set as a whole. If you look at the data set as a whole, most of it, surprise, surprise, most of it is just sensors. So if you just guess everything as sensors, you also get about 95, about 85, 86% accuracy, but the F1 score also suffers. This is next is random uniform, which is just basically everything has a 50-50% chance of being positive or negative label. And as a result, the accuracy is exactly 50%. And this is random proportional. So the idea is, if we look at the training set, training set, let's say 80 for every single label. So for example, there's I don't know, maybe something like 60% is sensors, maybe like 20. I'm just making up numbers, right? 60% sensors, 10% set points. So there's a 60% chance this will be positive. There's a 10% chance this will be positive, right? So that's the idea behind random proportional. And then 1 is the complete opposite of 0, where we guess, oh well, it is exactly everything's a sensor, as well as a set point, as well as an alarm, as well as everything else. And that is 1, which is exactly the opposite of 0. So yeah. So yeah. Finally, I think there are two more things that I want to talk about. One is the resources. Everything, as you can expect, everything is available in the AI crowd challenge page. To be fair, um, including all the different links to the old brick schema, including the starter kit will point to this GitHub, publicly available GitHub repo. We publish this dataset in NeurIPS, and you can see the archive version, the NeurIPS version, the one that's available on Open Review, the one I've been showing you. You can see the slides, you can see the posters. Yeah, so all the information is available there. One thing that you might find interesting is if you go to the accessing the data set, you can access the raw data of the training data. If you want to see what it looks like as a full building, the raw version is available here on Fixture, and then you can download it here. Um, and what's also available is if you want to know what does the full brick knowledge graph, not just the label, looks like. It is also, one of it is also available here, but just for one building. So the idea is this one building, side B, will be the easy buildings. You have the full knowledge graph. You have the full knowledge graph. You have the full data set, what it looks like, and then you have less information on the second building and less information on the third building. So it creates this kind of staggers of difficulty. And finally, that's the second last thing. All the resources is available there. The second last thing is the web conference. So this challenge is done as per usual, with some kind of conference. This one is done with the web conference 2025, and so the top submissions will definitely be invited to submit papers for presentation in the web conference. And that's everything from me. Thank you. I think if there's any question, I'll bring it back to Sneha.
Thank you so much for the presentation, Matt and Aryan. We will now move to the Q&A section. We already have the first question by Mo, who's asking, what does zero-shot forecasting do?
Sure. Yep. So basically, the zero shot this basically so when we're submitting a paper to NeurIPS or a dataset paper to NeurIPS, the idea is we want to show that this dataset works for many different tasks. One of it is the classification task, which is part of this challenge, and the other one is forecasting, which is not relevant to this challenge, but I'll still answer it anyway. The idea is the idea is the buildings data is very sensitive, right? If you have all the time series from the buildings, it is arguable that you can figure out of every single the schedule of every single person in the building, and that's have like a huge privacy issue. So so the idea of zero shot forecasting, long story short, the idea for zero shot forecasting is that if you want to make a forecasting algorithm for buildings, it has to be zero shot, and that means is people are very unwilling to share their building data with someone else. So the idea is it has to be trained on a different set of building, and then you package it, and then you sell it, and then the customer will get this algorithm that has been trained on other buildings, but on the buildings that they have, and it has to work there. So that's basically the idea of zero shots. Yeah.
I hope your question was answered, Mo. The next question is by Timur, who's asking, is the test set split to public, private, or not? Example, the metrics that we see on the leaderboard are from the whole test or not? Before that, I'm sorry, but before that, I think Mo has a follow-up question to his first question. Is it still a classification for zero shot?
Um, s- I I so it is well, I'm not sure I'm not sure what would no, so for zero shot forecasting, there's a forecasting task. So it's not nothing to do with classification at all. Yep. So it's not so the zero shot forecasting is a forecasting where you have time series and then you predict what the future is. Nothing to do with classification. And that's why it's like less relevant for this challenge. But all
Yeah,
the details is available in the paper.
yeah, like zero shot classification would be if you only have access to one building and then you try and classify on another building, right? Which isn't quite the situation that we have for this task.
What s- so for exa so for forecasting, this is very typical to time series forecasting, right? I'm answering the next question in the chat. What is being forecasted? What is being forecasted? Well, in typical time series forecasting is if you have time series, you're trying to forecast the exact thing, but in the future, right? So if it's a temperature sensor, you try to forecast the future temperature sensor. If it's a voltage sensor, you try to forecast the voltage sensor in the future. Yeah. I'll answer Timur. Uh, Sorry if I pronounce your name wrong. Um, is the test set split to public private or not? Example, the metrics that we see on the leaderboard are from the whole test. No, it is not from the whole test. It is the answer. Yes, it is split public private, and it's the split is about 50%, and the split is also not random. So for example, just like the way we talk in the way I describe, in the split between trained and test, the idea is you have a lot more data about site B, about one building in trained. So that's an easy building. The idea is because we want to generalize how good can you perform in a building with less information. And so there's a staggered setup there between the training and the testing. Same thing between the public testing and the private testing. There's also a similar staggered setup in the split, but the quantity is roughly 50-50.
He also has a follow-up question on is raw training data allowed to be used for the challenge?
Yes. Yes. So you are allowed to use the raw trade. Yes, it is you are definitely allowed to use the raw trading data. Um, I mentioned the self-supervised setup earlier. Yes, not the semi-supervised, weekly supervised setup, as typically common in semi-supervised. Yeah, you can definitely use the features from the test set to train or inform the how you want to make your classifier. Yeah. So the answer is yes. However, you're not allowed to use time series from any other data set out there. So yes, you're not allowed for to use the features of the time series, the features of the test, but not outside of this data set. Um,
The next question is from Leo. The heating demand sensor and cooling demand sensor in training set only have negative labels. Does the test set contain positive labels for these? Uh, yeah, I'm not sure how whether you can respond to that, but yeah.
um, S- yeah, yeah. Yeah, I'm not sure. I'm not sure. How can if I can respond to that without revealing too much. But yeah, there is a let's just say there's a possibility that the data that the test set contain positive label for this. Yeah.
Okay. Do we have more questions in from the participants who have joined this town hall? If
So
not, then perhaps we could move to the questions that we have on the forum.
Sorry, Sneha.
Yeah.
It took me a while to process Leo's question in my head,
Okay. Okay.
but the answer is the does the tested content positive labels for this? The answer is um, it might contain, but I want to elaborate that this goes back to the way I explained earlier how the data partitioning strategy is being staggered. So how the data partitioning is being staggered, and that is why some time series might not appear in the training data set, like a few amount of the classes might not appear in the training data set because of this staggered setup. Yeah. The answer is it might appear. Yeah.
Okay, then we can perhaps move to the questions from we have before we do that, I think Mo does have another question. Is there any difference between the data in two phases? In two rounds? I believe that's what he meant.
Yep. Uh, so in so it's very similar with the training and the testing. It's just the distribution. The distribution is different from which building and from which time, but the format is exactly the same. Yeah. You're welcome. No worries.
Okay, so the first question is from Ben, who says that he's familiar with the buildings and HVAC and controls, but he's curious if there could be any explanation for any newbies on how the models are put together, tested, and then optimized for MSc. And he also would like some high-level explanation on how the pros do this process until they have something fine-tuned that wins the competition. That would be neat. I'm not sure if we can just hand that response on the platter, but yeah, maybe you can take a stab at it and respond in a capacity you feel comfortable.
Um, I'm familiar with building. If there's any explanation on for newbies of how models are put together, tested, and optimized for MSc, I suppose band meant F1 score. That's what we use instead of MSE. Um, on how models are put together, tested, and optimized for MSE. Yeah, well, sure. I think I want I want to make this as accessible for everyone, including we are especially excited. We are equally excited for participants who are not coming from typical AI machine learning background, but from building backgrounds. And for that end, and to that end is if you go to the GitHub, um, and you go to the competition one. No, if you go to the class code, there's a number of code there available that I use to for this NeurIPS submission, it's available it's available there. Yeah. Um,
Yeah,
uh,
at least that's a really good place to start. But yeah, we can't give the whole secret sauce about how you make something to win the competition.
yeah. I mean, like, yeah, um, yeah. And if you go to the paper, I think if you go to the I think if you go to AI crowd, I think there's a link to paper with crowd, paper with code, right? If you're not familiar with this is a perfect place to start, right? So there's the repo, the GitHub repo, this link to the GitHub repo, and this link to the paper with code. This is basically a list of many different papers out there that comes with the code, and this links to time series classification. So this is an excellent place to start. Oh, sorry, I just realized I'm not sharing my screen. Um, I think what I meant, I just realized I'm not sharing my
Yeah,
screen.
I'll just stop my screen share and you can do it.
No. It's okay. I just put the link in the chat. If you go to the AI crowd page, it will give a link to this papers with code. Yeah, so this is an excellent place to start. Yep.
Yes, and I think the starter kit is pinned on the challenge page as well, right on top. So yeah, easy access right there. We can move on to our next question from Chan Jun Hao. He's actually on the call. So if you would like to unmute and ask the question directly, you're welcome to do so.
I,
Um,
I do think
think
that has
Yeah,
already been
okay.
answered. Yeah.
Then I'll just read it out. Is the distribution of labels in the training set the same as distribution of labels in the test set? Um, yeah, I think yes. So there was that question that for example, in the training set, heating demand sensor and cooling demand sensor do not have any positive labels, and it's impossible to predict for those labels since there is no data with one label to them, and we've already covered that. But does that mean that the test set will also have no instance of those two labels as class one? If that's the case, why are they included as labels from the start? So I think we have kind of covered this, but if you would like to revisit this and maybe give more context, that's up to you. Okay. Yeah. It's the same question. So it's already answered. I guess we don't need to revisit it then.
Oh yeah, I think the first part's already been answered. Just to
Yeah.
clarify, yeah, it's not the same distribution of labels. Yeah, that's probably the simplest way to say it.
Dave is asking, he hasn't participated in round one. Can he participate in round two? Yes, there is no specific criteria that you need to cross in round one to participate in round two. And it does not affect your overall ranking because the final positions will be decided on the scores from round two. So. Timer, do you have a question? Were you trying? We can't hear you. Your audio is not. In the meanwhile, if someone else has a question, they can either unmute themselves and ask it or drop it in the chat.
I will say I do appreciate someone trying to come off mute and ask it verbally. Very much appreciated.
Sorry, there's an issue with your audio. We can't hear you. Okay, so he has one more question on the test set. If you are willing to answer, should we expect that the hidden part of the test is more complicated and from a building that we have less data from?
Um, I'm not sure how to answer about more complicated, but I can definitely say there will be more proportion about the building that you have less labels from in the test set. Yes, because of the staggering, you have more labeled data from one building and then less labeled data from the other building. So there's an easy one and there's a harder ones. So the answer is uh, yes, you will have less data, but I'm not sure how to quantify complicated. Yeah.
And there's a follow-up question on whether the final scores are based on the hidden part um, of the data set.
The final score will be based on the combination of the public and the hidden part. Yeah. Um, yes.
We have another question from Mo. Time series length do vary a lot, some in the split based on observation or time split as well, and the buildings mix. The question is a little unclear. Would you like to unmute and ask the question, Mo?
Hi. Hi.
Hi.
Yeah, I'm just wondering, because I do find the time series length vary a lot, so I'm wondering whether the split of train and text is based on the observation of time series, or actually it's a kind of time split. So we may have one census data split based on time, so part of it will appear in train, and the other part of it may appear in text. Is it possible?
Yes. The answer, yes, it is possible that during the 3 years it will be split. Some will be in train, some will be in the test. Yep. And as I said before, the varying in length between the varies in length between 2 to 8 weeks is to vary between easy and hard. So there's an artificial cut. Yeah.
Okay, so the buildings data, like building A and building B, they are mixed in the text, right? So they're both present.
Yes. So there all three buildings are present in all three buildings are present in the training and the testing at different proportion. Yeah.
Um, okay, so because I noticed that some data on the building B, right? For building A, there is a map, right? For building B, the map is not disclosed. So about the knowledge graph, is it called, or the relationship, the hierarchy on building B, will it be disclosed sometime?
No. There's you only see the turtle file, the knowledge graph, only from one building. Yeah. It's in the GitHub.
Um, um, yeah, I see. Fine. Thanks.
No worries. You're welcome.
If we don't have any more questions, we can bring the first town hall to a close. It was quite an active session. I thank Matt and Aryan for their presentation. And thank you guys for joining from whatever time zones you guys are in on a Saturday. So thank you for taking the time out, joining this, asking your questions, and participating in this challenge. Thank you all for coming. Hope to see your submissions on the leaderboard, and we'll keep you posted with any updates and the next round. Thank you. Bye. Have a good day.